Now I'm going to explain the basic idea behind a motor or a generator. And I'm going to do this in terms of the fundamental forces. And we'll start by talking about the magnetic force on a moving charge. And here's the idea. Suppose we have two magnetic poles. Here's a north pole, and this is just one end of a bar magnet. And over here we have a south pole. So this is the south pole, another end of a different magnet. Well, in between, we're going to get a magnetic field. We have magnetic field lines that are going to go from north to south. And they'll look something like this. Now let's imagine a little positive particle over here that's moving. And it's going to move across this magnetic field in this direction. So what you want to picture is this moving into the screen. This is a perspective view, so it's going. Try to picture some depth to this graphic here. It's moving into the screen. Well, it turns out in this case the particle will be deflected down, and you can tell that by the right hand rule. If you turn your hand over and you point your fingers in the direction of motion, if this is a velocity vector here, v in blue, point your fingers in that direction and have your thumb pointed down. What happens is your fingers are pointed in the direction of the velocity, and they naturally bend. If you bend your fingers like you're cupping your hand, they will naturally bend in the direction of the field lines. And if you point your fingers in the direction of the velocity, such that they naturally bend in the direction of the field, then your thumb naturally points in the direction of the force. It turns out that any moving particle, any charged particle like this, moving across these magnetic field lines, or a charged particle moving across a magnetic field, will experience a force. And the direction is given by the right hand rule. So if you want to try to picture your hand here, you'd picture your hand, your fingers would be like this. Well, let me try that again. Fingers like this and your thumb pointing down, such that your fingers would naturally bend over in this direction. So your fingers are pointing in the direction of the velocity, such that they will naturally bend to point in the direction of the field. And then this is your right hand, so it's turned over, and your thumb is naturally now pointing down in the direction of the force that this charge would experience as it cuts across that magnetic field. So this charge actually moves in a path like that. Now if you picture a charge coming back here, moving across the field in the opposite direction, it's going to be forced the opposite way. It's going to get forced up like that. And again, you can picture your right hand here. Let me try that again. That's your thumb. And then your fingers. And so you've got your right hand pointed. I'll do one more here. Well, something like that. Your right hand is pointed in the direction of the motion, such that the fingers can naturally bend into the direction of the field. In that case, your thumb then naturally points in the direction of the force that particle will experience as it moves across the field. So it's this right hand rule again that gives us the direction. And it turns out that if these particles were negative instead, everything would be reversed. They would be pushed the opposite way. So this is just a fact that a moving charge in a magnetic field will experience a force. And I'll explain this in terms of fundamental forces. If you have a mass, we'll call it M, that mass has a gravitational field around it. And that's just the way the universe is. So this could be the Earth, and there's a gravitational field around it. And then if you take another mass, we'll call it little m, and you place it in that gravitational field, it will experience a force. It would be pulled toward the Earth. Okay, in the same way you can think about a charge. If you have an electric charge, so say here's a charged object, it has an electric field around it. And if you were to take another little charge, let's call it Q, and place it in that electric field, it would experience a force on it. It would be pushed by the electric field. So a mass in a gravitational field experiences a force. A charge in an electric field experiences a force. It turns out that a moving charge in a magnetic field will experience a force. So let's talk about the moving charge again. Here's a piece of wire, and let's imagine there's some current flowing through the wire, and I is the symbol for current. And so there's this magnetic field, and the field lines are these circular loops around the wire, like that. There's a magnetic field around moving charge. And the electric current flowing through the wire is moving charge. I'll draw some more lines here further out. If I were to take another charge, we'll put it here, call it Q, and have it move through the field, it would experience a force. A mass in a gravitational field experiences a force. A charge in an electric field experiences a force. And a moving charge in a magnetic field experiences a force. And that is the way the world is.